Good morning, everybody. Can everybody hear me? So I think we're about on time now, so I'll kind of go to normal speed. So I'm working with Joe Wong, who's also in the crowd, and Jim Evans, Paul, and then Professor Anna Arias in the EECS department, Professor Zodi also here on campus. We're also collaborating with a group at Cal Poly in order to really scale all this stuff up. So the first question is, why are we really looking at this tri-layer integrated solar energy cell with onboard storage? Why are we doing that? This is a graph for one wind turbine over the course of about a day. So you can see how you get peaks and valleys, and you've got moments where you do and don't have wind, and the problem gets even worse when you look at a solar panel. You have a cloud go overhead, and you can lose 80 to 90% of your power immediately. So how are we going to actually fix that? Right now, the way the grid works is you have peaker plants that are constantly running. The quickest ones take about 10 to 15 minutes to spin up. So in order to fill these gaps, we have to continue using fossil fuels, and they don't respond on time. So we need something in line. We need something integrated in order to solve this kind of issue. And when we look at what California actually needs is by 2020, we need 33% of the grid to have intermittent energy storage or energy sources like wind and solar on board. So without some way to balance out this load, we're going to have an unstable grid, or we're still going to have a major reliance on fossil fuels. So our printed energy storage is kind of branched off into two areas. I know Paul mentioned Imprint Energy, so they're doing a great job in doing small scale stuff. And now we want to move into the much larger realm, where you use flexographic printers like you see over here, which are much, much larger and also have a much higher throughput. So just real quick for everybody who hasn't seen Christine's work previously, and I know we've seen this slide many times, the custom dispenser printer. We've got inks to print the anode, cathode, gel polymer, all the different components of a battery. We can print those on a variety of different substrates. We can print them on current collectors. We can print current collectors and put that on different polymers and flexible substrates. And you can see just a cross-section here of all the particulates. So the performance in about May 2010 is about 1 milliamp hour per centimeter squared. And this is something that we can scale up. So we can actually be printing on much, much larger scales in order to increase the capacity. But we also have the ability, as we saw with Lindsay's integration with her energy harvester, that it can also be printed on smaller scales and still be able to function very well with the devices. So also something that's very important is that our chemistry, we're using a zinc carbon chemistry. Usually we know these as primary cells that don't recharge. Use it once, battery's done, you gotta throw it away. We're using an ionic liquid electrolyte, and that actually allows us to take these batteries, which have very cheap components, and we can recharge these. So this is at about 200 cycles with a C rate of about 1/2.5. So at about 200 cycles, we don't really see any degradation, which is fantastic. So we have really long cycle lives for these batteries. And I'll get into geometry and how cheap it is and why we're really pushing this. So what about scale? We see solar panels in a house. The house needs maybe 20 kilowatt hours. But then you can talk about really large farms, whether that's wind power if we just need storage, or when we talk about these solar panels where we still need on the megawatt scale. We need something cheap. Looking at all this stuff that currently exists, all the chemistries, you've got sodium, sulfur, but we know those have had problems recently with development, flow batteries and lithium ion. Everything seems to be pretty expensive at the moment. Our chemistry actually sits at about $100 a kilowatt hour. We've spoken with electric companies like Pacific Gas and Electric and Portland General Electric, and they're really aiming for about $100 per kilowatt hour is where you need to be in order to actually have something that people want to use and that you can deploy into the field. Anything else is just kind of outside the realm that's really feasible for the large-scale deployment. So with our chemistry, we want to be able to take it from the dispenser printer, where we have these kind of small-scale, relatively slow application, to much higher throughput, much faster deposition, printing, and manufacturing. So we can take our structures over here and print it, where every stage just prints every different component. You can print the ink, you can dry it, you can do different things to it if you need to, and you eventually end up with a full battery. And then with that battery, we can stack them. So let's say you have a device that maybe needs 4.5 volts, or maybe needs 3 volts, or some different kind of capacity. We can stack multiple layers of these batteries and these cells together to give you the power output and the voltage that you actually need to run it. And the main goal, the Holy Grail, would be to fully integrate, not just flexigraphically printed, but just printed electronic device. So we can have a printed solar cell, printed energy storage, and then printed circuits. Everything integrated together. Maybe it's in line like this in series, so you have one stage where you print the circuitry, one where you print the energy storage, and then you immediately roll into the solar cell. And then maybe you can have a parallel system where you print each of them side by side, and then you bring them all together into this one full device. But the idea is that each component can be printed and put together, so it can be flexible, cheap, and you can apply it to a lot of different kind of things. So we're focusing just on the printed energy storage right now. Professor Ana Arias is working on the circuitry and the solar cell applications. When we talk about cost for these things, let's talk about what a newspaper really costs. So this is the Piedmont Post. It's a newspaper in the area. So looking at the printing costs for about 2,200 copies. This is full color, including all of the different details associated with labor, man hours, materials, etc. Works out to about 16 cents per meter squared. Let's look at the chemicals for the battery. Adding all that stuff together, we get about $1.50 per meter squared. That's relatively cheap for a really large battery with a really good capacity. So when we break it down, it does come out to about $100 per kilowatt hour, which is right where we need to be for industrial applications. Let's compare that to some other stuff. I mean, we see grid scale flywheels. A lot of them are trying to be deployed right now. They're about $200 to $500 per kilowatt hour. But the issue is that you've got safety concerns. They can be rather large. You need a larger kind of install base. And it's even worse with pumped hydro. It's a great system. It's cheap, but you can't put it everywhere. Let's say you have a plane, maybe out in Arizona, you have a solar farm. Unless you have a large elevation difference, you can't install pumped hydro. So there are different locations where we actually need different kinds of solutions in order to really support the grid. So getting into some of the stuff that we've been doing with the inks is that the dispenser printed inks need different kinds of properties. They need a different viscosity, they need different particulate sizes. Flexographic inks have a different kind of requirement. So I'd say think about it in terms of like your toothpaste. So we need something that has particulates inside of it. You can squeeze the tube and it comes out nicely, but it still holds together on your toothbrush. It's the same kind of thing with the flexographic ink when we print it. We want this thing to print and hold together and not just smear out and spread all over the substrate. So about 6 to 9 months ago, we were in this area on the far left. So you've got the CMC and PVDF cathodes. Those are different binders. So they were relatively low, and we're aiming for what a graphic ink is, essentially something that you see on a newspaper that has the properties essentially of what like a toothpaste does. So now we're actually right in that range using a PSBR cathode, which I think he's somewhere in the audience, but Joe's done a great job developing the specifics of how we actually get to that point with the composite inks. And then looking at the performance of the batteries that we have, you can see that we've got it's about 13 hours for discharge with like a 0.1 milliamp current being drawn from it. And you can see it's a very nice, smooth curve. We don't have any discontinuities, and this can run for at least 100 cycles. So this is on a flexographic scale. And comparing that to like a AA battery, you've got a printed cell that we've developed that has maybe like 50 to 100 milliamp hours per centimeter cubed when we talk about volume. A rechargeable battery has around twice, but the problem is a AA battery cannot be printed like this. It can't be put on unique geometries like the moats that Andrew was discussing or the energy harvesting that Lindsay was talking about previously. You don't want to stick a AA on top of a MEMS device. That can totally change the packaging and the way that you design and think about your device. So this is stuff that we've done a couple months ago. So this is from Cal Poly. We've been working with them in order to get up to speed and to be able to help push us much more quickly toward a full-scale flexographic printed battery. So this is maybe 3 meters long. This was printed in about 4 to 5 seconds on a small scale test bed flexographic printer. So when we talk about full scale, we can print everything at incredibly high rates. So you can have a lot more batteries printed out, you can reduce the cost, and you don't need as many people watching it and having to modify different things. This can all be automated, and you can see from the inks we get nice edges. The geometry is really, really controlled. You can also print the electrolyte. As you see on the bottom, we're still doing some optimization with how we're going to really get the film thickness, but we're printing the electrolyte, and as you can see in the top right corner, you have a gel. That is the gel electrolyte that we're using. It's something that's robust enough where you can peel it off, pick it up, hold it, and pull it around, which is fantastic. We don't have these aqueous electrolytes that go everywhere. So essentially what we want to do now for the future work is we want to print this fully flexographic battery. This will be the first time that that'll be done. Something that we can now integrate with solar cells, energy harvesting, different kinds of motes, and all these different applications. We got to optimize some of the battery chemistry a little bit, because when we change the properties for the flexographic printer, that can modify some of the properties. So we're just optimizing that because of the new manufacturing directions. Looking at alternative materials, again, that's all optimization stuff. And then printing the current collector. So let's say instead of printing on just the, like a piece of foil, like stainless steel foil is what we're using now, we can print it directly on the back of a solar panel, or directly in line with a polymer substrate that a flexible solar cell is on. That way we have a completely printed battery with, on any kind of substrate you want. So the flexibility for the manufacturing process will be fantastic as we move forward. So we have those materials now, and again, it's really just getting to the point where it has all the electrochemical numbers that we're looking for on any application we need. So with that, that's kind of it. So thank you guys, and any questions?
Thank you, Rich. Open the floor for questions. We have one.
Thanks. Just really quickly, questions on, I guess this is applicability. When you speak of essentially storage integrated with a PV cell,
Yep.
You're mostly talking about, I come at this from the perspective of a grid planner.
Sure.
And so shifting PV generation to the post-sunlight hours is probably the most important thing. I guess I'll just caution, this is, it's compelling visually, but in reality, the geographic distribution of PV cells dampens a great deal of that variability, and so it's right. A little bit misleading to put this here. But what is more interesting to me is the potential to shift the shape of that to the right, as it were, as we look to the evening hours, and in particular air conditioning load and things along those lines. So I guess my question is really mostly focused on, have you looked at how this overall shape might change with a fully integrated storage and PV product?
So I know you mentioned pushing it forward and about this graph. I mean, maybe when you talk about full grid scale, I know that there are ways that people have looked at distributing the control systems in order to sort of alleviate some of these issues. But we've spoken with people at PG&E, and we've had meetings with them. And as far as the planning stage, they've talked about wanting to have things where essentially you can turn this into like a block where you have this beginning part as a block, and then this larger part as a block that you can essentially sell on the power market over time. So as far as shifting it forward, I don't foresee that as a major issue, aside from there being enough sunlight or surplus sunlight in order to charge it to be able to do something like that. But it ends up being more a question of how you want to integrate the circuitry, whether you want to have the battery directly in line with the solar cell, or whether you want to have it in series, so the battery's constantly being charged by the solar cell and the battery's constantly being discharged by the grid. So depending on how you want to set that up, as far as your standpoint for that, that can kind of change what this does look like at the moment and what you want it to look like. So when we talk about a fully integrated, like printed cell, I mean, this wouldn't necessarily be jagged like this, but it'll give you more flexibility for being able to control it and sell blocks of power.
That's helpful. I guess the shape that when we look at the sort of the aggregated grid need, when we look at renewables integration, you mentioned 33% earlier. The shortcoming of PV technology is that it really is peak focused in the sense that it's a coincident peak with sort of the largest of the air conditioning load. 10 years from now, I think the much bigger problem we're going to end up with is, say, 2 hours worth of ramping need in the very early morning before when your PV production is incredibly low, and 2 hours after PV production has subsided. And when we look at procurement of very large scale amounts of PV, storage is probably a very, very important part of actually allowing PV to compete with, say, fossil resources. So those, the areas before this and after this curve are probably the most important, and it's very compelling to see industrial process that could commingle the generation and the storage in a single platform. I will just ask that you think a little bit more about being able to charge from the grid during the nighttime hours to address that need and to be able to produce some of the blockiness before you see actual PV production. But this is very impressive.
Sure, thanks. I'd actually love to talk to you after this, because again, it's a lot of this stuff. These are things that we discuss with PG&E, and even they say, like, we're still trying to figure out, as far as power companies, how we're going to go about this. So I think I love that idea. I'd love to discuss that more with you after. Back.
Okay, we have 2 questions. Okay.
I was just wondering if you could clarify what it is exactly that you're testing, and to what degree is the focus of your research and your work, sort of assembly systems that deliver a product that is capable of, at $100 per kilowatt hour, and if that is sort of at least one area of your focus, what is the product? Is it an installation ready product? Is it something that is durable enough to be installed and in the open air, or is that where it will be? Right. I just had some general questions about sort of the end product or the focus of the research.
Sure. So that was originally the idea for the end product, was where we can say, okay, the grid needs a couple megawatts here, maybe a distribution center, or even the empty space under like a solar panel or inside of a wind turbine, like in the stem that's holding it up. Ideally, we were originally thinking like we can print all these cells very cheaply to hit that $100 per kilowatt hour price point, stack them to whatever the grid really needs, and then implement it like that. So it becomes more of a production-ready solution. So we've got a package thing that says, what do you need? We'll print it and then give it to you as like a block that you can install directly into the grid. Discussing with power companies kind of complicated that a little bit as far as what they're looking for. It's because we really wanted to know, like, what do you need? Because it's sort of like, instead of trying to solve 15 problems, it's like, oh, well, do we want to even this out, make it nicer? Do we want to have it in line? Do you need quick response versus slow response, like a capacitor versus a slow discharge battery? So it's a little bit of whatever the problem may be. These kinds of manufacturing processes and applications can be kind of modified to suit whatever that is. But at the moment, it's really, we're trying to just get the energy storage together. And this manufacturing process is well suited for integration with a lot of different other kind of printed processes. So while we are doing that integration directly with a lot of these devices, it's not beyond the manufacturing methods to print a full stack device that you just give like a large stack battery to somebody that's fully printed.
So I just had some questions that are along the same lines, but a little bit more detailed on the production process.
Sure.
So in particular, I was curious as to what the yield is. I mean, on the when you're printing these things, and whether you've looked at the structural stability of these devices with respect to things like twist and shear.
Right now, we're still focusing on a lot of the chemistry stuff, and as you mentioned, yield is definitely something that we're taking very, very seriously. We found that a lot of the issues as far as yield are concerned tend to deal with the printed electrolyte, and there are a lot of variables as far as that is concerned. We want to print these in open air, so we don't want to have a giant flexographic printer that's sitting in a giant argon glove box for lack of better equipment. So there's a lot of variability there. So at the moment, yield is, we're able to make batteries that charge and discharge and look like a battery, but we're trying to maximize the cycle life at the moment to be able to get it as far out as we possibly can. So we're still messing with the chemistry as far as that's concerned. And as far as the mechanical stuff, that is something that we're going to be doing once we have made fully flexographic printed batteries. Like, what is the maximum radius of curvature that you can bend this thing and twist it? And when we talk about stacking, depending on how we orient it, the bottom layer will support everything above it. So that's definitely a major concern that we will be looking at directly, but we don't have stacks large enough where it's much of an issue at the moment.